My name is Bill Manning, and that stuff looks out of focus to me even from up here. I'm going to talk a little bit about IPv6 addressing. I've been involved with it for a little while, and I'm going to pass on some observations about IPv6 and how it might be considered, because in a migration standpoint. That's one of the things that people talk about, is that there will be coexistence between IPv6 and our friend IPv4. So IPv6 is an awful lot like the blind man and the elephant. If you can grab it from one place, it looks horribly different than if you grab it somewhere else. So we're going to look a little bit at some of the history behind how the addressing structure has evolved, and hint at the fact that it's probably not finished. Look at some of the things that are happening actively inside the IETF. And then if you actually want to look at how somebody does this, how many people have ever touched IPv6 before? Are you happy? Would you be happy? Oh, never mind. We'll get to that. I'm going to show you a little bit of how we map in the DNS, basically the pointers, and it's really sort of useful to have the map because you have so much to deal with. And then look at some tools that are available, some things that still need to be done, and then some possible ways forward before IPv6 can truly be integrated into real systems as opposed to academic and experimental ones. Oh, when I get done with my sort of overview, then Akira Kato will come up and talk about IPv6 as deployed in a number of exchange points, which is kind of an interesting place to start. IPv6 really started as a huge number of bits, and there was some question about how do you structure that so that it's useful for people to use. And the IANA came up with, in conjunction with some of the addressing architecture guys, something that said, well, if we start off with this bit pattern, F5, and then you have some computation, you basically take your autonomous system number and you mush it around a little bit and stick it in these bits, and then the rest of it's yours to experiment with. That's a good way for people to sort of bootstrap IPv6. And that worked fairly well for a little while for people to actually get some understanding about how this should work. And they said, well, wait a minute, we really need to change the structure of the addressing headers. And approximately 15 months later, they came out with a new structure. And you'll see that if you see IPv6 these days. I don't think you'll see much F5 stuff running around anymore. But you'll see 6-bone stuff is very prevalent. The first set of bits is 3FFE. Shortly after that, they said, well, okay, this is great. This is for experimentation. You still have to apply through the IETF next generation transition working group chair to get a prefix under the 6-bone. They said, well, we really should get the regional registries involved because that's really where production stuff is going to happen. And so they carved up things called, in the format prefix and the TLA, they carved up these things called top-level aggregators. One of them is reserved for transition purposes. It starts as a 2002, 6-4, and they also carved out space for the various regional registries in the 2001:0 part. And what's under discussion now is shifting to the left, actually passing off to the regional registries how they can better allocate space left of the 64, or actually left of the 35. So addressing structures like in v4, in v4 it took longer. We went from host to network to classful to classless. In v6 we're going through some of the same types of things. It's already gone through several iterations. So in some sense it's relatively cooked. People are starting to develop products and services based on this structure. Shifting focus a little bit from the actual format of the addresses to how do you actually encode these things. I'm getting old. I can remember 32 bits most of the time. I cannot remember 128 bits unless you compress a whole bunch of zeros in the middle. And so contrary to a friend of mine who said there were no urgent DNS problems, with IPv6 there might in fact be, because if you can't remember the literal address, you might have to remember the name. So inside the IETF, they came up with some new resource record types in the DNS to sort of track this stuff, and they also started promoting native IPv6 transport. I'm going to touch briefly on one of the areas of concern with that right now. So we have new resource record types. We have the forwards, being the IETF and letting 1,000 flowers bloom. They said, well, we're going to give it our best shot. It's 4 times bigger than an A record. We're going to call it a quad A. It's been around for a long time, 96. Is that right, Paul? Something like that. But it doesn't really support renumbering easily, and that's one of the promises that v6 gives you, is that you really can divorce topology. So the end systems can sort of move around, you can change providers, you really don't care too much about what your actual IP address is because it can change. Quad A's are operationally, for those of us that use Emacs and VI for editing our zone files, it's operationally intuitive. It's just 4 times bigger. Again, over the course of some experimentation, they said, well, we really need something that supports better renumbering, so they came up with an alternative thing called A6. It's still 128 bits, but you can split it into pieces. It's really cool. But it's not been out very long. Operationally, it's kind of complex because you can't just look at the record and say that's the complete record. You can say, you have the potential of saying, I can look at a record and that's only a piece of it and there's a chain that I have to follow. You basically do, in the DNS parlance, additional section processing. That's a little bit hard for operations people to comprehend sometimes. From the reverse perspective, you have DNAME. It's not a whole lot more complex than CNAME. And you have bit strings. Bit strings are unique enough that it generates what are called form errors, and last time we checked, about 97% of the resolvers. So from the DNS, from the tools support stuff, things are just beginning to emerge that will help fix or help you manipulate and maintain IPv6 records. Unfortunately, if anybody remember the ISIS OSPF wars? Which one is the best IGP? Well, we have something similar here in that we have 2 types of IPv6 records that perform the same function, Quad A and A6. And there is some question about which one actually gets used in particularly constrained arenas, and this actually raised the sort of the important piece here, which is how do we deploy this in the DNS, in particular the DNS root context? Do we add Quad A's or A6s? Do we put v6 transport on? Do we stop there? How do we actually install this stuff? The question that was raised about which one actually created a tremendous amount of discussion inside the IETF as do we kill one? And if so, which one and why? And I don't know that they've got an answer to that yet. So there are a couple of things about doing a stepwise refinement, doing some staging, doing some merging of these types of ideas to actually see which one actually works best. On a good day, I like A6. On a bad day, I like Quad A. Inside the DNS itself, and for those of you sitting in the back, there are plenty of seats in the front to actually read this. What you have is the first few bits are called a format prefix, and it's 16 bits. And then you have the TLA, or the top level aggregator, and you have the next level aggregator, and then you have the secondary level aggregator. That's basically your top 64 bits. Some of those fields are reserved, and then you have the bottom 64. And so for this particular structure, starting at the bottom, we have 3FFE::/16. That is the format prefix and the top level aggregator for the 6-bone. It's a perfectly legitimate, in current addressing parlance, IPv6 space to work from. We have the next level aggregator right here, which is 3FFE:0800. /24. And what that is that's for exchanges. That's where it's marked at. And then we parse out things to various exchange points. The one in Los Angeles is 3FFE:0800 : a bunch of zeros /48. And then the individual machines that can sit underneath that are in this type of arena. It makes it difficult to actually type all this stuff in. So you really want to be able to use labels instead of numbers. But inside the DNS you have to do this. And it's appropriate. This is in fact copied out of our DNS zone file so that it helps you when you actually edit the file to figure out what's where. As things change, you'll find that perhaps those reserved bits and maybe the format prefixes may change their function as we evolve. IPv6, as I talked about, supports this idea of auto-renumbering. So you can take some of those top parts of the prefix, some of this stuff up here on this side, and you can change that. You can put in duplicate sets of entries, and you can say, well, I've got service from, I don't know, Bill's Bait and Sushi, and I've got something else from another service provider, Net99, right? And what you can do is you can leave the bottom half of your address intact, and you simply remap to pick the egress point. The problem with that is that doing dynamic renumbering of all the stuff in your network, there are things that really don't like that. If you're doing point-to-point links or tunnels, you really need to be able to identify those, and there are people that say, well, we can solve that in some other way. BGP peering is the same way. You set up the peer with the neighbor's IP address. And if you auto-renumber, then your BGP peer drops, right? DNS servers, you need to be able to keep track of where the servers are. Doing DNS server renumbering is problematic because you have all that stuff stuck in the resolvers. Basically, the problem is anywhere IP addresses, any application which depends on hard-coded IP addresses is going to have problems. So while IPv6 looks like it's pretty good, operationally it's still got a little ways to go. From a registry perspective and from how people actually deal, does anybody here deal with a registry for getting numbers? Nobody does? Oh, well then I can skip this time. Registries tend to want you to document your use of address space. And you can either do things like SWIP, which I think is evil incarnate, or you can use RWHOIS, which is only slightly better. A couple of years ago, some folks at ISI put IPv6 support into RWHOIS, so it is possible to maintain your delegations in RWHOIS if you've got them. Now, Bind 9 has all of the wonderful new RR types. It has a couple of performance considerations, principally due to, as someone told me, buggy POSIX stuff with threads. If you actually go to the registries and you say, fine, give me an IPv6 prefix, they'll give you one. And then you say, can you map it, please? Can I put a name server up on native IPv6 space? And they'll go, wait for about 3 to 6 months, because their internal tools are structured around 32-bit addresses. So maybe by the end of the year, the registries will be ready. Now, the Americas, as somebody pointed out, Americans are capitalists. IPv6 you probably aren't going to make a lot of money on. Europe and Asia, they're either more forward-thinking or they're more desperate, or they see this problem differently. But they are much further along than the Americas in adopting and exploring, looking at what it takes to put IPv6 into their networks. And it's desirable, if you have extra cycles, to start looking at this. As someone at a little meeting this morning at breakfast pointed out, IPv6 customers are starting to ask for it. So even if you don't have a solution today, it's appropriate to investigate what your choices are so you can give them an answer. So I'm going to defer questions. And Akira, if you could come up. Akira Akira Kato comes from Japan, where he built a thing called NSP IXP6. If you do any sort of peering overseas, you will have dealt with Akira.
This is Akira Kato from Wide Project Japan, and I'm now working with the beer mining at USCISI until this autumn. So I'm going to present regarding NSP IXP6 very shortly because the timing is running out. And there are several activities in Japan to develop IPv6, and operational requirement is getting growth. In 1999, I think, Wide is willing to host the experimental exchange in Tokyo to accommodate those IPv6 related activities. And we put the separate switches from the production IPv4 exchanges called NSP IXP2. NSP IXP6 is named after that exchange point. But the reason why we split into this is that the NSP IXP2 was not able to accommodate the IPv6 ports because the no ISPs until still no ISPs are running dual stack routers. So people put the V4 router here and V6 separate V6 router here. So there is no reason to migrate into single exchange point, but we separate two exchange points. And the place is in some telco facility in Tokyo so that people are able to connect the purchasing just a UTP or fiber in-house so that they don't have to pay IPv6. They don't have to pay a circuit for IPv6 only. And topology is that we have several switches in Tokyo, and also we are able to provide the access through the ATM, which is some portion of the NSP IXP6 is available to across the JGN, which is the Japanese government-funded testbed ATM network, which is very similar to BBNS in this country. And also, we are able to have a VLAN extension to Osaka. So we also try to deliver the exchanges, IPv6 exchanges to some events like INET 2000 or IPv6 Summit in Osaka. So the topology is like here, maybe the number in the parentheses is shows the number of the ISPs which are connected to that particular switch. And I don't know where total number of ISPs is something like 20. And this is one of the most active V6 exchanges in the world, I think. And this is traffic. So this graph shows that IPv6 is no longer for ping or trace route. Some people, the number is very small. However, some people already started to use IPv6 for his production purposes. And so the daily average traffic, maybe some of the people may see the red line in this graph. Daily average traffic is about 200 kbps or something like that, and which is the 1,000th of the current V6 or V4 environment in Tokyo. Or in other words, V6 internet is maybe 10 years behind V4. And we are going to replace the more bigger switch because many people are asking us to connect the NSP IXP6, and still it's experimental and separate from NSP IXP2. And there's no harm. The IPv6 introduced no harm to IPv4 environment. We are going to provide the V6 and the V4 production quality exchanges at NSP IXP2, which is the current V4 exchange. And we got the web page www.azjp.nspexp6 and pretty strong access. And in this country, there is several exchanges available, and one of the most innovative activities is the 6IIX, which is the being provided by telehouse people. And there is a set of IPv6 exchanges. The one is New York, maybe 25 Broadway, and they have some plan to extend 60,000, where 6 staff will be there. And they're going to hold the Santa Clara and Los Angeles. And the Los Angeles wide and USCISI appearing in IPv6 natively already. And Sugeno-san from Telehouse is now planning to the layer 2 extension of 3 locations. Okay, the URL is here. The other exchange is Pikes. Unfortunately, I cannot see any basic description of the brochure of Pikes, but maybe there are substantial activities out there. And 6TAP is one of the very famous V6 exchange at layer 3. And there are several activities also in Europe. And those exchanges are available at the webpage www.v6nat.net.
Just a little correction on your slide. The PAX actually doesn't use a separate switch. You can do the V6 peering on the regular switch.
Oh, it's the same one.
Yeah, it's the.
Oh, I'm sorry.
Okay, just a small correction.
Okay, thanks a lot. So, anyway, that's it. Do you have any questions? Thank you.